Hey everyone, welcome to the last video of Chapter 9, 9.8, Systems of Linear and Quadratic Equations. Our goal is that we can solve systems of linear and quadratic equations. Now, you can hopefully remember that in the previous section, 9.7, we talked about linear, exponential, and quadratic equations. Today, we're actually going to be combining some of the knowledge that we talked about in the previous section, and we're going to see what happens when a linear function and a quadratic function cross paths or intersect. So we can solve systems of linear and quadratic equations graphically and algebraically. There are three different possibilities for solutions. The first possibility is two intersection points. Remember that a solution means how many times the two graphs intersect. That's what a solution means. So the first option is 2 times. The second option is only once, so one solution. And the last option is no solutions at all. That means they never cross paths or intersect. So today we're going to be looking at how to solve a system of a linear equation and a quadratic equation using graphing as well as algebra. So first, in example 1, we're going to graph these two equations. And what I'm going to do is use 2 different colors to hopefully help you decipher which one's which. So the first function is a quadratic. It's x squared minus x minus 2. First thing I would like to do is try factoring. So I set up the x method, and you can do the same. And the numbers that work to multiply to get negative 2 but add to get negative 1 are negative 2 and positive 1. So that tells us that we can factor and get this and equals 0. Remember, we're trying to find the intersection points on the x-axis. They're called the roots or the zeros. And we set each of these equal to 0. We practiced this in this chapter. And just do the opposite. So plus 2, you get x equals 2, and then minus 1, x equals negative 1. So that tells me right here that these two numbers are the x-intercepts of this parabola. So immediately go to the graph and put 2 points. One at positive 2, one at negative 1. And also another thing that we know immediately is that the y-intercept is equal to negative 2. Remember, it's always the c value of the quadratic. So now we can go to the y-axis and go to negative 2, and that is the y-intercept. Couple more things we need to know. The vertex. The vertex would be really helpful, and I think after that we can just connect. So remember, how to find the vertex, you have to use minus b over 2a. So I guess I'll squeeze it in over here, if it'll let me. Vertex x equals negative b over 2a. The b value is negative 1, and the a value is positive 1. So that means we have negative 1 over 2 times 1. That's a positive 1 up there, so we get 1/2 for the x-coordinate. And in order to find the y-coordinate, you just plug this in for the original function. So 1/2 squared minus 1/2 minus 2. So I'm going back to the quadratic. That is 1/4 minus 1/2 minus 2, and that equals negative 2.25. So the vertex is the coordinate 0.5, comma, negative 2.25. So go over to the graph. The axis of symmetry is always the x-coordinate that we found, so it's at 1/2. And the vertex is on this axis going down to negative 2.25. So about there. So we know that on the axis we can flip the points reflecting to get the other side. So that tells me that I have that point as well, and we are good to connect now. And actually, you may be wondering what happens above the axis. That would be a good question. We'll talk about that right now. So let's try -2 on the x-axis. Let's plug that in and see what number we get. -2 squared minus a -2 minus 2. That gives us 4 plus 2 minus 2. That equals 4. So another coordinate on this parabola is -2 comma 4. So let's plot that. And we know that we can reflect it onto the other side as well. So now we are good to put some arrows at the end, and we have our parabola graphed. So the hard part is done. Now let's graph the line. This won't take long. So we know that it is a line, mx plus b. M equals -1 and b equals 2. So that means we start at 2 on the y-axis. We always plot the y-intercept first, and then use slope knowledge. So you go down 1 over 1, down 1 over 1. Down 1 over 1. And remember, you can go the opposite direction, up 1, left 1, up 1, left 1. And you see right there that we have 2 intersection points. Connect, arrows at the end, and the last thing is identify those 2 intersection points by writing the coordinates. I'm just going to highlight them for you so it's super obvious where they're at. Now let's write down the coordinate points and we'll be good. So the first coordinate point is 2, 0, and the other coordinate point is -2, 4. So I'll just write in parentheses, these are the intersection points. So as you can see, this takes a bit of time, and you're wondering to yourself, of course, yeah, there's another method, and yes, there is. So let's talk about those other methods. Algebra. In this example, we're going to be using elimination, and I actually made this problem applicable to you guys. I'm sure most of you have been to one of the pools in our city. So let's read this together. Since opening day, attendance at Euclid Avenue Pool has increased steadily, while attendance at Osborne Park Pool first rose and then fell. Equations modeling the daily attendance y at each pool are shown below, where x is the number of days since opening day. On what days was the attendance the same at both pools? What was the attendance that day? So we have 2 equations, and you can tell that the first equation is linear and the second equation is quadratic. We're going to be using the elimination method. Hopefully you remember we used elimination several chapters ago when we solved linear systems, 2 lines crossing. This time we're going to be using the same process, however it will be a little bit different since we have a quadratic. So step 1, eliminate y. So we want to write down the 2 equations. I'm going to put the quadratic one first. And we will write the linear function. There is no x squared value, so I'm going to leave that space blank. And in order to eliminate the y, we must subtract. So y minus y is 0. X squared, -x squared minus nothing is -x squared. 39x minus 28x is 11x. And 64 minus 4 is 60. So you can see that we have a quadratic. And now we want to factor and solve for x. So let's, first of all, factor out the -1. Do you see how there's a negative sign in front of that quadratic? Let's factor out the -1 to make that positive. Then we can use the x method. So now we have -11x minus 60. Now let's use the x method on the side, -60 up top, -11 on bottom. What numbers work? Write out the factors. 1 and 60, 2 and 30, 3 and 20, 4 and 15, and 5 and 12, and 6 and 10. Which numbers would work well with 11 when you add? 4 and 15 are popping out to me. Now I just have to figure out, how do we get a -11? Well, if we have a +4 and a -15, then we get negative 11. So let's go back and write 0 equals negative 1 times x plus 4. So we're taking these two numbers and putting them in parentheses like usual. X minus 15. Now we want to set both of these equal to 0. We talked about the zero product property a few sections ago. So that means one of these guys has to be equal to 0 in order to multiply to get 0. Minus 4, x equals, it's not letting me write, x equals negative 4, that's a possibility, or x equals positive 15. Now, in step 3, we want to look at these two numbers and think to ourselves, does it make sense to have a negative amount of days? And the answer to that is no. So step 3, eliminate impossible solution, which is the negative 4. So the pools cannot be open a negative number of days, so x cannot be equal to negative 4. And now we're going to use the other answer, positive 15, to find the corresponding y value. You can use either equation. My suggestion is to use the linear equation because that is the easier option. So I'll show you how to do that now. And it does work for both equations because they cross paths, so it has to work for both. So let's take the linear equation and plug in 15. Y equals 28 times 15 plus 4, that equals 424. So the pools had the same attendance on day 15, and on that day they had 424 people at both places. Let's write that conclusion sentence and move on to the last problem. Let's try one more problem. In the textbook, the book shows you how to do this problem using substitution. However, I looked at that on page 598 of your textbook if you'd like to write that down, and I think that it's easier to use elimination. So I'm going to use that just to be consistent and also in hopes to not overwhelm you with another method. Now you can feel free to check out by yourself on the textbook online or when you are with me together during class. So let's use elimination. You're welcome to use either method. However, like I said, elimination is the easier option. So first, let's rewrite the two equations. You want to always have the quadratic on top, and fortunately it is that way. And remember, we want to line up the like terms. So the negative x right here needs to go below the x, so we might as well put a 1 in front to help you. And then the positive 4 goes below the 10. So now we want to subtract down. So we have y minus y equals 0. X squared minus nothing is x squared. Negative 6x minus a negative 1x, that's actually just plus 1. So that would be negative 5x. And 10 minus 4 is 6. So now we have this nice quadratic, and fortunate for everyone is that the x method works perfectly here. So let's write 6 and negative 5. The numbers that work, well, the only options are 1 and 6 or 2 and 3. And 2 and 3 work, but they both must be negative in order to multiply to get a positive, but add to get a negative. So let's rewrite that. 0 equals x minus 2, x minus 3, and let's set both of those equal to 0. X minus 2 equals 0, or x minus 3 equals 0. Add 2, x equals 2, or add 3, x equals 3. So we find out two values for x. Now we want to find the corresponding y values, and remember you can use either equation. But if you can recall from the previous example with the swimming pools, the linear equation is much easier. So let's take x equals 2 and plug it in. Y equals 4 minus 2, which equals 2. Goodness. Okay, so that means our first coordinate is 2, 2. And then let's also take the x equals 3, plug it in. Y equals 4 minus 3, which equals 1, so our other coordinate is 3, 1. So that means the solutions of this system are 2, 2 and 3, 1. So there you have it, elimination. Hopefully it's getting a little bit more comfortable for you. We will stop there. Feel free to try to lesson check for 9.8. If not right now, wait until tomorrow. And make sure you have 9.7 lesson check done. We will begin reviewing and practicing for the final pretty soon. So make sure you come with questions tomorrow.